Thank you for watching this video. In this video, I'd like to talk about acquiring dynamic light fields through a coded aperture camera. I first mention what is a light field. A light field is usually represented as a set of images taken from many different viewpoints, and it is used for various applications such as 3D display and depth estimation. To acquire a light field, several approaches have been investigated, including multiple cameras, lens array cameras, and coded aperture cameras. In this study, we focus on a coded aperture camera. This camera can acquire a light field with high spatial and angular resolutions. However, in previous works, coded aperture cameras were used exclusively for static light fields. We aim to extend the previous works to dynamic light fields. Our achievement is summarized here. Using a coded aperture camera, we can acquire dynamic light fields with fine quality as shown in the video. To successfully handle scene motions, we developed a new configuration of image observation called V-shape observation. And we trained the CNN using a dynamic light field dataset with pseudo motions. First, we mentioned the previous work of Inagaki et al. For acquiring a static light field using a coded aperture camera. This slide shows a schematic diagram of a coded aperture camera. Here, we assume that the target light field consists of 5x5 views. We can control the transmittance pattern of the aperture plane as shown below. Here, each square on the aperture plane corresponds to a single view in the light field. Using a grayscale pattern for the aperture, we can obtain a weighted sum of all the views. We can acquire a few images using different aperture patterns. Then, from these images, we computationally reconstruct the original 5x5 views, that is, the original light field. Here, we illustrate the case where we acquired only 2 images. The entire process is interpreted as follows. The original 25 views are first encoded into 2 images, and then decoded into the original 25 views. This process can be regarded as an auto-encoder, where the encoder corresponds to the image acquisition process, and the decoder corresponds to the computational reconstruction. The parameters of the encoder directly correspond to the transmittance patterns for the aperture. In the previous method, this auto-encoder was implemented using a deep CNN, and the encoder and decoder were jointly optimized through end-to-end network training. When applied to a real coded aperture camera, the encoder process was conducted as a physical imaging process on the camera, and only the decoding process was conducted on the computer using a pre-trained decoder network. From now on, we extend the previous work to dynamic light fields. We mention why this extension was difficult. First, we assume that the target scene is static. We acquire a few images using different aperture patterns. The difference between the images corresponds to the disparity information. From this information, we can reconstruct the original light field. However, if the target scene is dynamic, the difference is caused not only by the disparity, but also by the scene motion. Therefore, reconstruction of the light field becomes more difficult. To address this problem, we introduce 2 key contributions. The first one is a new configuration of image observation called V-shape observation. Here, we show a diagram along time to explain V-shape observation. We assume that 2 aperture patterns are alternated along time. The images are acquired using either of the 2 aperture patterns denoted as A and B. Our proposal is to use 3 acquired images denoted as 1, 2, and 3 to reconstruct the light field at time 2. The images acquired with different aperture patterns include both disparity and motion information. Meanwhile, the images observed with the same aperture pattern include only the motion information. Therefore, we expect that using these 3 images is helpful to successfully separate disparity and motion information. A dynamic light field can be acquired by repeating this reconstruction along time. We call this method V-shape observation because the locus tracing the 3 images constitutes a V-shape. Now, we go on to the second contribution. We trained the CNN on a pseudo-dynamic light field dataset. In the previous work, the network was trained on a static dataset, but we have to train the network on a dynamic dataset to adapt to the scene motion. However, there are no public dynamic light field dataset suitable for our purpose. So, we created a pseudo-dynamic dataset from static datasets. As shown in this slide, we clipped out 3 slightly different regions from a single image. By using clipped images, we can give pseudo-motions to the static scene. We assume that the motions are linear and have a constant velocity, and we created 25 motion patterns. Next, I mentioned the detail of our network. We adopted an encoder-decoder model to formulate the light field acquisition process. In the encoder part, the coded aperture is modeled as a 1x1 convolution filter, similar to the previous work. The parameters for this filter correspond to transmittance of the aperture pattern. In the decoder part, the target light field is reconstructed from the 3 acquired images using many convolutional layers. This is a summary of the training details. The training was conducted with 5x5 and 8x8 viewpoints. This is the aperture pattern for the 5x5 viewpoints, which is optimized through the training process. The optimized patterns are different depending on the method due to the difference of the observation patterns in the training dataset. We can see that the aperture patterns are partial and complementary to each other, so that the acquired images should contain much disparity information with each other. We evaluated our proposed method by simulative experiment. For quantitative evaluation, we prepared a computer-generated dynamic light field using POV-ray. This light field contains motions with various velocities in various directions. We compared our method against several other methods. The training dataset and the number of images used for reconstruction are different method by method. This graph shows the average PSNR for 5x5 viewpoints along time. The horizontal axis is time, and the vertical axis is reconstruction quality. Reference corresponds to an ideal case where the light field was reconstructed from 2 images observed with different aperture patterns at the same time. This is practically impossible, but can be used to show the upper bound reconstruction quality. Some of the methods are designed without considering scene motions. These methods show poor reconstruction quality. Meanwhile, our V-shape method exhibited the best reconstruction quality among the methods tested here, and its performance was even close to the reference. This graph shows the reconstruction quality for 8x8 viewpoints. Here again, our V-shape method achieved the best quality. This video shows reconstructed dynamic light fields. The heat map located in each result shows the PSNR of each viewpoint. Our method achieved good reconstruction quality consistently over all the viewpoints along time. This is the result for 8x8 viewpoints. Again, the best reconstruction quality was achieved by our V-shape method. Finally, we evaluated our method using a real coded aperture camera. This slide shows the experimental setup. We implemented 2 methods, our V-shape method and Inagaki's method. These videos are reconstructed results. The left panel is our V-shape method, and the right is the previous method. Here is a close-up to show the details. We can see that our method is superior to the previous method. Here is a conclusion of this talk. If you are interested in our work, please visit our website. Thank you for watching this video.